The AKS Primality test is not all that it's cracked up to be. What do we mean by that? Well, the AKS Primality test is a deterministic algorithm for determining if a number is prime that runs in polynomial time. Sounds kind of complicated already. It is an explicit polynomial time deterministic algorithm. It's known as the AKS Primality test. Now, we don't really believe that it is such a great test. Notice here, it has an infinitesimal chance that the algorithm might return an ambiguous result, meaning that maybe you get a prime number, maybe it's not a prime number, and maybe it's not accurate at all. To determine whether a simple number like 31 is prime or not, you have to go through all of this here, flip it over to another page, and go through all of that. There's a much simpler primality test. It's known as the Shujinski-Manigault primality algorithm, shortened for the process proof. Process is Latin for moving forward. And you're going to see that this proof moves forward. It proves whether any prime possible number is a prime or not. Prime possible we designate as a capital P and a smaller case p. We note that decimals indicate whether that prime possible number is prime or not. And you will see in just a moment what we mean by that. Granted, this looks complicated, but it's not as complicated as this. This is sophisticated, as is the AKS test, but this is sophisticated in a simple, deterministic way. The AKS test doesn't appear to be so deterministic as they claim it is. So how does this process proof work? Well, we start with the indication that we've got a prime number. We determine whether it's prime by this process right here. This is the proof. The step number one. Prime is determined by whether the prime possible number, we take the square root of that, and if there is a decimal involved, we eliminate that decimal, and we determine a cynosure square. The cynosure square is the upper bound, and by upper bound, we mean that we're not going to go past the cynosure square. Step number two, we have the prime possible number. It's divided by the cynosure number 3, then the cynosure number in the following column, and then in the next column, and we proceed in that fashion until we reach the square root of the prime possible number, which is very much close to what we would call the cynosure square. That is the upper bound. We stop there. Step number 3. If you divide that cynosure number into the prime possible and there are no decimals, that means that those two cynosure numbers combine to create the prime possible, and therefore you have a non-prime number. Step number 4. If a prime possible number divides by any of the cynosure numbers up until the upper bound, which is a cynosure square, and it produces a decimal, this indicates that you've got a prime number. Decimals indicate a prime number. If this cynosure number divides into the prime possible, then it is a multiple of the prime possible, and a prime possible that has multiples other than 1 and itself. Those are non-prime numbers. So the process proof is a lot simpler than this AKS primality test. If you wanted to use the AKS test to determine if 31 is a prime number or not, you'd have to go through all of this here, and you would see that the output is prime. 31 must be prime, and it's kind of a must be probabilistically, at least it appears to us that way. The sequential primality testing, the SPT testing, is derived from the definitive infinitary. On page 26, we begin with predicting the primes. The SPT is entirely deterministic, and you can see it before your very eyes. Okay, what do we have here? We have the cynosure numbers, 1, 3, 7, and 9. These cynosure numbers produce columns, which we call the cynosure columns, 1, 3, 7, 9. Now, if you're thinking the sieve of Eratosthenes, that's good thought, but this is much more sophisticated than the sieve of Eratosthenes. This takes the sieve of Eratosthenes and gives it a lot of mental muscle. How does sequential primality testing work? Well, you pick a number. Let's pick the same number that is in this paper here, 31. We take the square root of 31 and we get 5 and some change.
5.56 and change.
5.56 and some change.
Mm-hmm.
Well, we have to eliminate all of that change because we want to get close to a cynosure number. Now, lower than 5 and some change, we get to 3, which produces a cynosure square. 3 times 3 produces 9. So we know that this is the upper bound. 3 is the upper bound. So if 3 divides into 31, then you know that 31 is not a prime number. But if 3 divided into 31 produces decimals, then 31 is a prime number. Now, how do you know for sure? Visually, how can you prove this? Well, to prove this, you would need to follow the patterning that produces non-prime numbers. These non-prime numbers, how are they produced? Well, you can see very easily that they are produced in this fashion. 3 times 7 gets you here. Oh, but we forgot the cynosure square. 3 times 3 produces 9, which is the first number that is not prime. 3 times 7 produces 21, which is the second number that is not prime. 3 times 9 produces 27, which is the third number that's not prime. 3 times 11 produces 33, another number that's not prime. 3 times 13 produces 39, another number that's not prime. 3 times 17, well, that's off the chart, so we already know that 31 is a prime number because none of the numbers in the cynosure columns multiplies together to produce 31. That's the process proof. It proves by moving in this direction, by multiplying these cynosure numbers by each other to produce non-primes, we know that 31 is a prime number. The upper bound is the cynosure square, 9, which is 3 times 3. How did we get to that 3 times 3? Well, we took the square root of 31 and we got 5 and some change. 5 brings us back to here. Where is the closest cynosure square? Well, that's 9, produced by 3 times 3. So this is the cynosure square that gives us the upper bound. We can see that after this cynosure square, the next cynosure square, 7 times 7 is 49, that's way beyond 31. So this cynosure square, since it's beyond 31, this is the upper bound. It cuts off at this cynosure square. Any other cynosure square after 31 is excluded. So you can see that the process proof works by compressing the possible primes into a specific range, the range between 3 and 31. Here we have a cynosure set from 1 to 100, and we're going to see how this process proof works. Well, we've got our cynosure columns 1, 3, 7, and 9. So prime numbers are going to be located in those cynosure columns, with the exception of 2 and 5. Why 2 and 5? Well, because 2 and 5 are so very close to the origin that there are no possible numbers that can combine to produce 2 and 5 other than 1 and 2, 1 and 5. So 2 and 5 are prime numbers. They're in yellow because they are prime numbers, but we exclude them from the cynosure columns. We consider 1 to be a prime number. That's because 1 can be divided only by itself, 1, and 1, which is itself. So 1, in our estimation, is a prime number. We also like to think of 1 as a prime number because it is within one of the cynosure columns, 1, 3, 7, and 9. The process proof relies upon locating a number within one of the cynosure columns, taking its square root, and determining the cynosure square below it. So if we were to look at, say, the number 63, we would take its square root and we would find that the cynosure square below it is 7. So that would be the upper bound. So 7 here would be the upper bound. So we would start with 3 and see if 3 divided into 63. Instantly, we see that it does. 3 times 21 divides evenly into 63. There are no fractions involved. So we could stop right there. What about 73? Well, the chart indicates that it's a prime number, but let's say that we don't know that 73 is a prime number. Well, we take its square root, we find out that the closest cynosure square is again 7. So now we go back to 3. The process proofs begin with 3. 3 divided into 73. Does it produce a fraction?
Yes.
Yes, it does. So we'll still continue. 7 divided into 73, does it produce a fraction?
Yeah.
Yes, it does. 9 divided into, well, wait a minute. We don't have to go to 9 because the cynosure square below is 7. 73 is a prime number. We know that the upper bound is 7 times 7, 49, because that's the cynosure square immediately below 73. In 2 steps, we indicate with the process proof that 73 is indeed a prime number. Here, we are looking at the cynosure set from 101 to 200. We know that all prime numbers must live within the cynosure columns. This column is the column 1, 3, 7, and 9. The digits end in 9, the digits end in 7, the digits end in 3, the digits end in 1. So these are the cynosure columns. All prime numbers must live or exist within the cynosure column. Let's try the number 183. Let's pretend that we do not know that it is a blue box and that it is therefore a non-prime number. So we've got 183. Instantly we want to see whether it is a prime number or not. So we take its square root and we find that the cynosure square closest to it is 13. So that is our upper bound. We stop at 13. Going back to the lowest cynosure numbers in the cynosure columns 1, 3, 7, and 9, here's where 13 is. So you can see that these cynosure numbers, all we have to do is progress from 3 to 7 to 9 to 11, and we stop at 13. 3 times 61 is 183. One operation, one division, determines whether 183 is a prime number or not. It is not a prime number because it doesn't produce a decimal. Here we have the cynosure set from 201 to 300. Let's choose as a prime possible the number 297. Now we know we take the square root of 297, the closest cynosure square is 289, 17 times 17. We know that 17 is the upper bound for 297. So what we do is we go back to the cynosure number 3, we divide 3 into 297. Lo and behold, 3 divides into 297, 3 times 99 produces 297. 297 is not a prime number. If there were a decimal involved, we would have to continue because we would have to eliminate all cynosure numbers up to 17. We eliminate 297 as a prime number instantaneously because 3 times 99 gets us to 297. Here we have the cynosure set from 301 to 400. Now let's take 399. We find the square root of 399 and the closest cynosure square is 19. 19 is the cynosure square that is closest to 399, the possible prime. So we start at 3. We divide 3 into 399. Instantly, we see that 3 does divide evenly into 399. 3 times 133 produces 399. There are no decimals, so we can stop right there. 399 is not a prime number. Here we have the cynosure set from 401 to 500. Let's pick the number 469. This is a possible prime. So what we need to do is take its square root and we locate the cynosure square beneath it, which is 441. And now we have 21 as the upper bound. Now we must go in sequence here. That's why it's the process proof. It goes forward from the first row of cynosure numbers to the second row, third, fourth, and fifth, and so on and so forth, starting with the cynosure number 3. We see if 3 divides into 469. 3 does not divide evenly into 469. It produces decimals. So at this point in the process proof, we know that 469 is still a prime possible. We know that 21 is the upper bound for the prime possible 469. We already tested 3, so now we're going to test 7. We divide 7 into 469. 7 divides into it evenly. 7 times 67 produces 469. 7 multiplied by 67 produces 469. There are no decimals involved, so we have discovered a non-prime number. Here we have the retrorsum proof. Retrorsum in Latin means in reverse. So how does this work? Well, we would like to locate a prime number. We derive whether it's a prime number or not from this process here. We start with the prime possible, we take its square root, and we determine a cynosure square. We proceed in reverse until we arrive at the cynosure number 3. Once we get there, and all of these numbers in reverse divide into the prime possible and produce decimals, then we know for sure that that prime possible is a prime number. First of all, we start with a prime possible. We are going to determine whether it's a prime number or not. We take its square root, and if that square root produces a decimal, well, we have to eliminate that decimal to discover the nearest cynosure square below it, below the prime possible number. That is the starting point from which we will divide into the prime possible, looking for a decimal. If there are decimals, it's prime possible, and we continue in reverse. The second step, the prime possible number is divided by the cynosure square. If you produce decimals, prime possible. We continue. Move to a column lower, then move to a column lower than that, and we progress all the way back to the cynosure number 3. You notice that -1 column means decrease by 1 column the cynosure number that you're looking at. Step number 3. If a cynosure number divides into the prime possible and it eliminates decimals, there are no decimals, then that prime possible is a non-prime number. Step 4. If the prime possible number, when you divide it by a cynosure number, moving in reverse, it produces a decimal all the way from the cynosure square back to cynosure number 3. If there is a decimal to all of those divisions, you've got a prime number. We have already indicated that the AKS test is kind of complicated. And it probably takes a lot of computing power from your computer. Here is our high-value primality testing. You can use the process proof or the retrorsum proof. Here we have chosen the numbers 487 and 46,784,321. Obviously, you can choose cynosure numbers much larger than this, but just for a quick example, we're going to focus our attention on 46,784,321. Okay, what do we do? Number 1, choose the cynosure number. We just did, that big number. Take the square root, the cynosure square we want to discover. So the square root of 46,784,321 is approximately 6,839.
0.9.
0.9, okay. So we leave off the decimal, and that is our cynosure square. So if we use the retrorsum proof, we would have to start at 6,839 and work our way backwards. But here, I would like to use the process proof. We have already discovered the cynosure square. That is 6,839. So we round that cynosure square to a whole number, ending in 1, 3, 7, or 9. Well, 6,839 ends in 9, so that will be our upper limit. Now we begin the algorithm at that number if we're going to use the retrorsum proof, and we go in reverse. But just on a hunch, I would like to use the process proof, and that begins at 3. So, we eliminate products of cynosure numbers. So is 46,784,321 a prime number? Well, if I use the process proof, I would have to start with 3, divide it into that large number, 46 million plus. Then I'd have to use 7, and then 9, 11, 13, 17, 19, 21, 23, 27, 29, 31, 33, 37, 39, and 41. By the time I got to 41, I would see that 41 divides evenly into 46 million plus. Here, we can see that 41 times 1,141,081 produces 46,784,321. So because 46,784,321 is divisible by 41 and this large number, 46 million plus, is not a prime number. Let's look at the prime possible 487. Let's try an even newer way to determine whether a number is a prime number or not. Let's take a look at 487 in a different light. Let's determine within the range around 487 whether the cynosure numbers around it are prime or not. Now, why would we want to do that? Well, if we locate, let's say, a cynosure number that is not a prime number, say, for example, 477, we see that it is a multiple of 3 times 159 and 9 times 53. So we know that using 3, we can determine whether 487 is a prime number or not. 3 times 159 produces 477. 3 times the very next cynosure number, 161, gets us over here. And you can see what's happening. 3 times the cynosure number after 161 is going to get us here. So we've gone past 487. So 487 is prime possible. We notice that just before 487, we've got 9 times 53. So 9 times the number that follows 53, 57, is going to get us off the board. So 9 and 3 are already eliminated. So we have to work our way up to 21. 21 we can see is over here. 21 times 23 gets us here. 21 times 27 is going to get us off the board. We have eliminated 3 and 9 and 21. 21 is the upper bound. So now we need to eliminate 7, 11, 13, 17, and 19, and we will know for certain whether we have discovered a prime number. Now we're looking at 7. 7 times 63 gets us here. 7 times 67 gets us to 469. 7 times 69 gets us to 483. 7 times 71 gets us to 497. We have passed 487. So now we know that 3, 7, 9, and 21 do not divide into 487. We proceed to 11. We've got 13, 17, and 19 to go. If we determine that 487 doesn't divide evenly by these numbers, we have a prime number. Using the cynosure number 11, we are going to try to determine whether 11 goes past 487 or not. 11 times 41 produces 451. 11 times 43 produces 473. 11 times 47 is off the board, so 487 is very much prime possible. From 11, we move to 13. 13 times 37 produces 481. That is just below 487. 13 times 39 is off the chart. We have 17 and 19 to test now. 17 times 27 produces 459, which is below 487. 17 times 29 produces 493, which is above 487. 17 does not divide evenly into 487, so 487 is very much prime possible. So now we have to look at 19. 19 times 23 produces 437. That is below 487. So 487 is a prime number. Many of the materials that you saw today can be discovered in the definitive infinitary. You will see that there's also a visual proof of the Riemann hypothesis. On page 26, you will find an entire section dealing with predicting the primes, deterministically predicting them, not probabilistically. So there's no margin for error here. The techniques in the definitive infinitary will predict primes exactly. No probability. Precisely. It is the definitive deterministic algorithm locating prime numbers.